everyone, and welcome to Precalculus. This is the third video on section 5.2. It's just a bunch of problems being worked out for you. There's nothing new being taught on this video, but in case you need to see some more examples, I'm going to be working them out from a worksheet. I'm doing numbers 9 through 16, 19, 21, and 23. So the first thing that I always want to do is draw a line so I don't accidentally work on both sides. And then right away, I see that 1 minus sine squared alpha, and I think, oh, that's the same as cosine squared alpha. That's one of the Pythagorean identities. And then one of the quotient identities is sine over cosine is tangent, so sine squared over cosine squared is tangent squared alpha. And now I'm going to switch to the other side. While you may recognize this, if you don't, the one that's a little bit more recognizable is that 1 plus tangent squared alpha is secant squared alpha, and then the two 1's cancel, and you just get tangent squared alpha also on this side. And this one is done. So remember, I did this two different ways. On this one, I replaced the secant squared with 1 plus tangent, where on this side, I knew this variation of the original identity, sine squared theta plus cosine squared theta is equal to 1. So you have a choice whether or not you want to know several variations of the identities, or whether or not you just want to know the main one, 1 plus tangent squared alpha is equal to secant squared alpha, and then substitute that in. So a couple different choices there. Number 10. So this time I actually think I'm going to work on the right. I see one denominator, but two terms in the numerator. So I'm going to try splitting that up. Secant of alpha minus secant of alpha over secant of alpha. And then this is nice. This becomes 1. And a cosecant on the top is the same as a sine on the bottom. And a secant on the bottom is the same as a cosine on the top. Those are our reciprocal identities. And then cosine over sine is cotangent of alpha. Remember, I'm just showing you one way to do these. There's lots of variations. Number 11, I start by drawing my line down the middle. I see this as a really obvious identity, so I'm going to go ahead and write that one right away. But this is the more complicated side, so I think I want to actually work on that side. I'm going to start by another strategy, which is changing everything to sines and cosines. That secant, another reciprocal identity, is the same as 1 over cosine. A secant on the top is the same as a cosine on the bottom. That allows me to cancel, and I get sine squared theta on both sides now. And this one is done. Number 12. Again, I have a lot of different things going on, and last time I chose to simplify that 1 minus cosine squared, but because this is a sine, I'm actually going to leave that. This Greek letter is pronounced either phi or phi. So phi is in Phi Beta Kappa, pretty famous honor society, but you can also pronounce it phi, which is actually how I pronounce it. So sine of phi plus cosine of phi, and then I'm going to change that cotangent to cosine of phi over sine of phi. So when I first did it, I thought, oh, good, that'll cancel my cosines, but the cosine's actually on top, so it doesn't. But now I can change that to cosine over 1. Remember, it's easier to multiply a fraction by another fraction than by a whole, because people get confused. So if you make the cosine phi over 1, then it's easy to go straight across your numerator and straight across your denominator. So I kind of look ahead a little bit, and I see that this is a 1 over sine of phi. So I think to myself, well, how can I make this one over sine? I can give it a sine of phi on the top and on the bottom. It's really important, if that's going to be your step, that you show me that that's your step. And then that gives me sine of phi over sine squared phi over sine of phi. Now they have a common denominator. I can write it as sine squared phi plus cosine squared phi all over sine of phi. Not 2 sine of phi. You don't actually add them. Just like when you have 1/2 plus 1/2, you don't actually add them, right? Or multiply them. It stays the same denominator. So, and then here's the last identity you need to do. Sine squared plus cosine squared is 1. And I'm done. I write this one again on the other side, and it kind of gives some completion to it. Number 13. Now, a strategy that I've given you in the past is that whenever you have two terms and you have to make them into a single term, it's always going to involve a common denominator. Shouldn't have used that word always, because this one's not. And this one, I'm going to do my other strategy, which is changing everything to sines and cosines, because a secant squared on the bottom is the same as a cosine squared on the top. And then you can either recognize that this is sine squared beta and be done, or if you still don't know that, the 1 can be replaced with sine squared beta plus cosine squared beta, and then minus your cosine squared beta, and then you do get sine squared beta. I'm going to bring sine squared beta down onto the other side, and then I am done. So hang in there with me. This one's a lot of steps. So first, I have the problem of two terms becoming one term. So my instinct tells me to get a common denominator. But simultaneously, I also don't like that I'm mixing secants, tangents, cosines, cotangents. So I kind of feel like I should be using the strategy of changing everything to sines and cosines. So I'm going to kind of do a mix of that. First, I'm going to change this secant to a cosine. A secant on the bottom is the same as a cosine on the top. Now I already have a cosine on the top, so now I'll have two of them, so I'll have cosine squared beta. And similarly, using another reciprocal identity, a tangent on the bottom is the same as a cotangent on the top. So if I put that cotangent up there with the other one, I'll have cotangent squared beta on top. And this is so close to what I want and yet so far, because this one's being subtracted and these are being multiplied, but they're otherwise the same. How does that even happen? So now I'm going to go back to my same concept, that the only way to get two things into one is to get a common denominator. So the way to get a common denominator, you need a denominator. So I'm going to change this one to cosine squared over sine squared. Cotangent and tangent are my two quotient identities. And now, make sure you show this step. I'm going to multiply this one by sine squared beta on the top and the bottom to give it a common denominator. So now they have the same denominator, and this one is sine squared beta, cosine squared beta, minus cosine squared beta. And this would be very tempting. All the time I get kids who just cross off the cosine squareds, but you can't. That would be like saying that 2x minus x is just 2. It's not. Okay, you can't subtract away an x. If it's being multiplied, you can't subtract it away. But what you can do to it is factor it out. You know I love factoring. So this becomes, if I take out the cosine squared beta, sine squared beta minus 1 all over sine squared beta. So I could scroll down, but so you can keep seeing this, I'm going to just move it to the top of the other side here. So now I want to do two things. One is I want to take that cosine squared beta over sine squared beta, and I want to kind of make it on its own. It's not a common denominator. This is a tricky concept for kids. But if you have x over y over z, I can make that either x over z times y, because think about it, that would be over 1, and you could go straight across the numerators and straight across the denominators, or x times y over z. So you can put that z under either one of them individually. What you can't do is x over z times y over z. that would equal xy over z squared. So you can give it to one of them if you want to. Little algebra background there. So I'm going to give the sine squared just to the cosine squared, because with a little foresight, I can see that that's going to make cotangent. So that's going to become cotangent squared beta. And then on this one, this is one of our identities. So maybe you have it written down as sine squared beta plus cosine squared beta is equal to 1. If that's the case, then you can replace this with sine squared beta minus, and then you can put that whole thing in for 1. Sine squared beta plus cosine squared beta. A little complicated. Some of you might have every single possible form of this written on your paper, in which case you would have sine squared beta minus 1 is equal to negative. And that's why I said you might not have this one because it's a little bit more obscure. But sine squared beta minus 1, you'd have to move that cosine to the other side and it would be negative. This is a problem that students really love to fudge. And I will catch you because you already have the answer. I know where you're going to get stuck. So I'm going to be looking at this step pretty carefully. But if you were to distribute that negative, the sine minus the sine would go away, and the negative distributes to the cosine, and you would have that. Now, it's not subtraction. It's just a negative value, which I can move out to the front and change their order around just so it looks the same. Okay? Really, really, really tricky problem. I'll just put a box around it. And then ironically, we move on to 15, and it's nowhere near as hard. But I chose 15 because it practices one of the strategies that I talked about, which is multiplying by the conjugate. This Greek letter is pronounced lambda. So secant of lambda minus, I started to write plus there, but it's minus tangent would be the conjugate. Minus tangent of lambda. And people ask me all the time, can I just switch them all to x's? No, you're taking precalculus. You need to learn how to say and use lambda. So on the top, I didn't draw my line. I'm going to give myself a little more room here. Secant of lambda minus tangent of lambda times cosine of lambda all over, and if I FOIL that out, I'll get secant squared lambda minus tangent squared lambda. Now that might be on your list of identities, but if you only have it written as its original, which is 1 plus tangent squared theta is equal to secant squared theta, then you would just replace that secant squared lambda with 1 plus tangent squared lambda minus tangent squared lambda, and that whole denominator just becomes 1. But you might have it written down that secant squared minus tangent squared is equal to 1, and then you'd skip this intermediary step. I'm going to distribute, even though it's on the back side there, you can still distribute. So I have secant of lambda cosine of lambda minus tangent of lambda cosine of lambda. And then the bottom is 1, so I can almost cancel that out, but I'm just going to rewrite this step so I don't lose anybody. But now that I can write it without the 1 there, I'm going to change my secant to 1 over cosine. That's a reciprocal identity. And I'm going to change my tangent to sine over cosine. Notice I don't always say lambda every time, but I always write it. I will take off if you don't write it. So then these cancel, and I just get 1. And then these cancel, and I just get 1 minus sine of lambda, which, even though it's all the way back up there at the top, was what I was looking for. 1 minus sine of lambda. All right, number 16. As usual, I start with making my line. And then right away, I see 1 plus cotangent squared alpha, and that is an identity. It is the same as cosecant squared alpha. which is perfect because I have a cosecant of alpha on the bottom. So just like x squared over x becomes x, cosecant squared alpha over cosecant alpha becomes cosecant alpha. And then we've got a nice straight up reciprocal identity. This is 1 over sine of alpha. I'm going to write it on the other side to give it some completion. But wow, compared to 15 and 14, that one was a piece of cake. So they don't always get progressively harder. Number 19 is on here because I want to talk about factoring for a minute. Remember, as another strategy, that if you're looking at something and can't factor, think about it as x's and y's. And hopefully when you do that, you can see that this is cosine squared alpha minus sine squared alpha times cosine squared alpha plus sine squared alpha. So this is a particularly hard one for students because this part of it literally just goes away. Cosine squared plus sine squared is just equal to 1. So a lot of times people will do little things like that. The correct way to show that step would be like this, times 1, and then cosine squared alpha minus sine squared alpha. Just so you know, I don't really want you to do, I do this sometimes in the video to make sure everybody's understanding me, but the correct form of a proof would look like this. So now I still have a problem. I have all cosines on this side, but I still have a sine over here. Well, that's okay. You can always get rid of a sine and change it into a cosine if it's squared. You can't do this unless it's squared. And sine is the same as 1 minus cosine squared alpha. So that gives me cosine squared alpha minus 1. I'm distributing my negative, plus cosine squared alpha, which is 2 cosine squared alpha minus 1. So like I said, sometimes people get confused because what happened to this part of it? I ended up just working with this part, and that's because it's equal to 1. Number 21 is on here because I wanted to show you how to get a common denominator. The biggest mistake I see is people doing this. 1 minus sine of, got that lambda going again, and then 1 plus sine of lambda. I will take off points for this. This is not correct. Whatever you do to the top, you have to do to the bottom. And because the whole point of this is a proof and you're trying to show me, even if you squeeze it in like that and don't make it an extra step, I'm okay with that. But I need to see that you've done something to the top and the bottom. So now this becomes cosine alpha minus, not alpha, lambda, cosine lambda minus sine lambda cosine lambda all over. Now if you multiply that out, that becomes 1 minus sine squared lambda plus, now distributing that cosine, this one is cosine lambda plus sine lambda cosine lambda. And that is also all over 1 minus sine squared lambda. I'm just going to go ahead and draw my line over here since that took up so much room. And then I can put them all over the same denominator, but I'm going to do 2 steps at once. 1 minus sine squared is cosine squared. And when I put these all together as 1, I'm going to have 2 cosines, but this negative sine cosine and this positive sine cosine cancel. So I have 2 cosine lambda, which now one of these cancels with one of these, and I end up with just 2 over cosine of lambda, which is what the other side was. And I'm done. Okay, last one. So right away, I see that I have sines and cosines on the left, but only cosines on the right. So immediately I think to myself, how can I change that sine into a cosine? And hopefully you remember that you can only do it when it's squared. Sine squared plus cosine squared is equal to 1. And then so your other arrangements for it are that 1 minus cosine squared is equal to sine squared. And that's what I'm going to be using. You can change a sine to a cosine. If you have a squared, you can make it 1 minus cosine squared. Oh, but I don't have squared. I have sine to the fourth. So this rule doesn't apply to sines to the fourth. Please do not write 1 minus cosine to the fourth. Okay? Easy mistake to make. Instead, let's factor that. Let's think of that as x to the fourth minus 1. How would you factor that? Hopefully, x squared plus 1 and x squared minus 1, which is what we're going to do. When you want something that's to the fourth to be to the second, think factor. So we have sine squared theta plus 1 times sine squared theta minus 1 all over cosine squared theta. And now I'm going to replace sine squared. So I'm thinking about this, and I replace the sine squared with 1 minus cosine squared theta. That plus 1 is still there. And I'm going to replace this sine squared theta with 1 minus cosine squared theta minus 1. So now I'm partway there because I've gotten the whole side of this problem to be strictly in terms of cosine. And now this one and this one cancel. So this one becomes 2 minus cosine squared theta. That's a good thing. I see that 2 on the other side. And this becomes negative cosine squared theta. So this next step is a little tricky for some people because it's trig, but think about it as a regular number. If you had 3 over negative 3, what is that? Negative 1. If you had negative 21 over 21, what is that? Negative 1. So if you have negative cosine squared over cosine squared, what is that? Negative 1. So these two cancel and leave you with negative 1. And that's being multiplied by 2 minus cosine squared theta. I distribute the negative 1 to both of them, and I get negative 2 plus cosine squared theta, which of course, by the commutative property for addition, I can just switch those around. And that's it. There's so many more problems to try, but I think that hopefully this will be enough to get you going on section 5.2. Have a great day.